Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2017 Unit 1, Paper 2, and specifically, we will be doing a question on rates of reactions. So the first question, which is from question 5, part A, reads, explain each of the following terms. And the first term is the rate law. Now, we know that a rate law is the mathematical expression which tells us how the rate of the reaction changes in relation to the concentration of each of the reactants. Okay? So the second term that we're supposed to explain here is order of reaction. And the order of reaction is the power to which each of the concentration, right, of the reactants is raised in the rate law. Okay, so let's move on to 5 part B now. 5 part B says parts B, part I to B, part 3 refers to the following reaction. So here we have a reaction where we have A moles of X plus B moles of Y goes to products. Okay? So for this, we're supposed to write an expression for the rate law. So here's what an expression for the rate law for such a reaction could look like, right? So here we have our rate law, which we said earlier is the mathematical expression that relates the concentration of our reactants. Our reactants are X and Y. So we're relating those concentrations to the rate, right? How do these change the rate? And then we have the powers to which they're raised, which is known as their orders. And here we've written the order of X as A and the order of Y as B. But we know that we would have to determine A and B experimentally, right? We generally can't just use the stoichiometry or the mole ratios to figure out the order, okay? We would have to find the value of A and B experimentally. So this is our rate law, and we've also captured the orders there. Okay, and of course we have our rate constant K there as well in the rate law. Okay, so moving right along, we need to now write an expression for the overall order, Here we have the order with respect to X being A, and we have the order with respect to Y being B. So the overall order is just the sum of the individual orders. So the overall order will be A plus B. So that's an expression that we can use whenever we're asked to calculate overall order. Okay? Now, we're being told that the overall order of this reaction, so that's this reaction, which has this rate law, the overall order of that reaction was found to follow second order kinetics, right? Second order kinetics, the overall order. So now we're being asked to deduce the units of the rate constant for this reaction. Okay, so let's take some notes here. So we're being told that the overall order follows second order kinetics, right? And so what that means is that the sum of A plus B is equal to 2, right? So the sum of A plus B is equal to 2. So that's the first piece of information that we have here. So let's bring that up. So we know then that the overall order is 2. So A plus B is equal to 2. Therefore, it means that A is equal to 1 and B is equal to 1. Why? Because we know from the rate law that it has to include X and Y. And so we have to divide the 2 between both of them. So we make A1 and B1. The only other way that the overall order could be 2 is if one of them were 2 and the other 0. But we know that that's not the case because based on our expression, we know that we have to have both of the reactants present there. And so we divide the 2 between the 2 orders that are present, making A1 and B1. Okay? But the question is really asking us to determine the units of the rate constant K, right? K from here. And so to do that, what we're going to do is we're going to rearrange this rate law, making K the subject. And so we'll end up with this expression here that says K is equal to the rate of the reaction divided by the concentration of X times the concentration of Y. And remember, they're individually raised to 1, and so we don't have to write the 1 there. It's understood that the 1s are there, okay? So this is our expression that we have for K now. And from a unit level, right, the units of rate, we know is generally mole per dm cube per second, unless told otherwise. That's the rate that we work with. So I know that the units of my R, which is in the top, will be this. And then in the bottom, I have the concentration of X, which is in units of mole per dm cube. And I have the concentration of Y, which is also in mole per dm cube. So when I simplify these out, right, I'll realize that my mole dm cube in the top, that's coming from my rate. So let me get a pencil to show you that. My mole per dm cube in the top will cancel with one of my mole per dm cubes in the bottom. And so I'm left with this second here, and that's what I've shown coming over here. That's in the top. And then in the bottom, I'm going to be left with a mole per dm cube. So that's what I've shown in the bottom here. Now, to make this nicer and put everything on one line, I can bring up my mole, which is raised to the power 1 to the top, and that becomes mole to the minus 1. Right? So that's that mole to the minus 1 that I brought up the mole to the 1. It became mole to the minus 1. I can bring up my dm to the minus 3 to the top as well, and it will become dm cubed. And I just leave my s to the minus 1 at the top where it was. And so that's my unit of K. Okay? All right. So moving right along, let's clear this. And moving right along, so question 5C. 5C says the decomposition of gaseous nitrogen 5 oxide exhibits first order kinetics and is represented by the equation, and they give you 2 moles of nitrogen 5 oxide in the gaseous form is getting decomposed to 4 moles of nitrogen dioxide gas and a mole of oxygen gas. And what they're saying is, so let's just summarize the first statement here. The statement here is saying that this process overall exhibits first order kinetics. First order. So right away, I can write an expression for my rate law. And I would write R is equal to my rate constant. And it's going to just be N2O5, right? My nitrogen 5 oxide. And that is raised to 1. That's the only thing that's going to be my rate law. This is my only reactant. So it's the only reactant that I can write beside my K. But most importantly is that I have to only raise it to 1 because the question tells us that the reaction, which is this, exhibits first order kinetics. So I can only raise that reactant to a power of 1 in the rate law. So this is the rate law that we're working with for that reaction. Okay, so let's go down a little bit further now. A proposed mechanism for the reaction is made up of the following steps, where W and Z are intermediates. So here's our first step in that proposed mechanism. We have our nitrogen 5 oxide getting decomposed to W and oxygen gas. We then have this intermediate W going to Z plus nitrogen dioxide. We then have this intermediate Z combining with 2 moles of nitrogen 4 oxide to give us 3 moles of oxygen gas and nitrogen 5 oxide, 1 mole of nitrogen 5 oxide. So those are the proposed steps in a mechanism for that decomposition shown here. So now we have to use the information relating to the kinetics of the reaction to write the equation representing the rate determining step. Okay? Give a reason for your response. So we have to pick out of these three. Out of these three equations, which one represents the rate determining step? Okay, so we already know what the overall rate law is. It's this, right? And so what that means is that this rate law came from a rate determining step, the rate determining step. It came from the step where only 1 mole of N2O5 was being converted to some product. And that lands us right here. That lands us at the very first equation in that mechanism. So really that lands us here. It has to be this equation that represents the rate determining step or the slow step, right? It has to be that, and that's because this is what is reflected in the overall rate equation or rate law. Okay, remember, the rate determining step is what sets the stage for what the rate law has to be. You can only go as fast as your slow step, and so your slow step is what reflected in the rate law. And so if I were to write the rate law for this slow step, it would in fact be R is equal to K, parentheses, concentration of N2O5 raised to 1, because there's just only one of them there, okay? So remember now, a key thing to remember here is that whenever we use reaction mechanism to come up with a rate law, the rate law, the power, in this instant and this instant alone, when we're using a reaction mechanism, the power or the order comes from the number of moles of the species that's involved or the reactant that's getting converted in that slow step. And so that's why I would land on this rate law, and that matches the overall rate law, because these two things go hand in hand. The rate law of my rate determining step will be the rate law of the overall equation. And so let me just populate those here. So here is the equation. It's this one that represents the rate determining step. And here's my reasoning. So since we know that the overall reaction follows first order kinetics and that the rate law comes from the rate determining step, this reaction is the only one that matches that. Okay, so let's move along. So now we're at 5D, and 5D says that data for the decomposition of nitrogen 5 oxide at 333 Kelvin is presented in the table below. So here's our table. We have pressure of nitrogen 5 oxide remaining in units of Pascal, and we have rate of reaction in units of Pascal per second. And we have just some values there, 4 data points there. Okay. So we have to plot the data on the grid provided. So you would have been provided with a grid in the exam that you have to plot this data on, circling the plotted points as an X with a circle. Okay, so you're circling your X, which would represent your plotted points. So let's talk about that part first, so part I. If we are plotting the data on the grid provided, we have to know what we're putting on our y-axis and what we're putting on our x-axis, because they didn't tell us, right? So we have to be able to figure it out now, right? And so you may remember from the previous parts of this question, so part C, right? You might remember that the rate law went something like this, right? It was R is equal to the rate constant times the concentration of N2O5. But now we're saying in this data table that the concentration is pretty much a pressure, right? So what do we see here? What we're seeing here is that the pressure, we're looking at the rate law describes how the rate changes with the pressure of nitrogen 5 oxide, right? And so the rate, right? The rate will be my dependent variable. So I'm going to plot that on my y-axis, and the independent variable will be my pressure. Remember, the rate law says we're figuring out how the rate is affected by pressure. Okay? So the pressure is going to be on the x and the rate on the y. Okay? So let's go ahead. I went ahead and plotted that up nicely. And so this is what that plot looks like, okay? So here's our plot. On our y, we have rate, which is our dependent variable. And on our x, we have our pressure, which is the independent variable. And so we have a nice little straight line here, and I've drawn a line of best fit going through most of the points. So this is the plot that we were expected to draw there for D part I. Now, once we've drawn the plot for D part I, we're then expected to use the graph that we just drew to calculate the rate constant, which is K, for the decomposition of nitrogen 5 oxide at 333 Kelvin, stating the appropriate units. Okay? So when I look at my graph, what I'm realizing is we have to figure out what feature of my graph will give me the rate constant. And so what we then have to do is say, okay, we need to know that as it relates to the rate constant, right? So let's write that. So we're gonna write back the equation now. So R is equal to K, and that's a pressure, right? Even though I'm keeping my square brackets, we now know that that's a pressure that was measured based on our data here. So here's my K, right? Remember we just said that we plotted the rate on the y-axis and we plotted the pressure on the x-axis. So the K then nicely resembles a slope, right? If we're looking at the equation of this line, then that I so nicely got, a straight line, then my slope will be represented by K. Okay, the slope represents K. So that's y is equal to mx. And remember now, the formula for slope is rise over run. Okay? So I'm gonna have to draw a nice big triangle to calculate my slope. And my y2 will be my rate at a point. So let's just write R2 then, and then minus R1. And then my x2 will be my pressure at a point 2, and then my pressure at a point 1. And that will give me my K, because that's K, okay? And then what you might realize then immediately from a unit standpoint is that ultimately I will be having my rate, which is in Pascal per second, divided by my pressure, which is in Pascal. And so from a unit standpoint, the Pascals are going to cancel. And so my units of K will end up being just second to the minus 1. Okay, that will be my units of K. So let's go back to the graph and find the slope, and that will be the actual value of K, which is our rate constant. So let's go back to that graph real quickly. All right, so here's our graph, and here is the graph with some points chosen for the slope. So this is my big triangle that I drew here, right? So this is my big triangle. And I just had to go across up here to find my y2, which I found to be 0.83. Choose a different color. So I found my y2 to be 0.83, and I found my y1 to be 0.14. Right? When I came across here, I got 0.14. And so when I came down for that point up there, I found that my pressure at this point, that's corresponding point, was 960. And then I found that the pressure at this corresponding point for the lower part of my triangle was 160. So this 160 is my x1. This 960 would have been my x2. This would have been my y2, and this would have been my y1. So remember now what we said? We said that we have to do y2 minus y1 over x2 minus x1. So rise over run. That's going to give me my slope, which is also my k, right? So my y2 was 0.83. Subtract off my y1, which was 0.14, and divided that through by 960, my x2 minus my x1, which is 160. So then I'm going to get 0.69 being divided by 800. And then when I do that through, I'm going to get a value of 8.6 times 10 to the minus 4 seconds to the minus 1. And that is my rate constant, K. And so with that, we've come to the end of this question from June 2017. It was question 5. If you've made it this far, definitely give this video a like, subscribe to this channel, share it with your friend, and definitely stick around, hit that notification bell, and we'll see you in the next video.